This question is about isomers with the molecular formula C5H10O. Draw the skeletal formula of a branched chain. So we want sort of something with a branch on it like that. Aldehyde, so with the C double bond OH, which in a skeletal formula just ends looking like this. With molecular formula C5H10O, that is optically active, so has a chiral centre. So again, I'm going to do a bit of working out, then cross it out. So a chiral centre means a carbon with 4 different groups, and I know that one of them is going to be an aldehyde. I know that I've got 5 carbons altogether, and there's already 2 here. I'm going to put a H onto one of these so that I can make it optically active, and I'm going to put a CH3. That leaves me with 2 carbons, and I need it to be branched. Okay, so this is already a branch, this carbon here, because we've got 1, 2, 3, 4. So this is probably my structure. So I'm going to make my skeletal formula. So a 4-carbon aldehyde. So 1, 2, 3, 4, and then my aldehyde. And then on the second carbon, my chiral carbon that's making it optically active, I'm going to have a branch. And I'm just going to cross through my working out. Describe how you would distinguish between separate samples of 2 enantiomers of the branched chain aldehyde C5H10. So how would you distinguish between the 2 different optical isomers? And they're optical because of their effect on light. So we're going to use, and it's not just any type of light, plane polarized. So that's light traveling in only one plane. Plane polarized light. Each enantiomer, and what they do is they rotate the light in opposite directions. So one rotates it clockwise, the other anti-clockwise, by an equal amount. Draw the E and Z form, so that is when we have a carbon-carbon double bond, with each carbon having 2 different groups, of a structural isomer that shows both optical and geometric. So it's got to also have a chiral carbon. Okay. Now, if it's going to have a C double bond C, it can't have a C double bond O. So we're going to swap that O to being saturated. We're going to make it an alcohol group. We do need to still have a chiral carbon. So let's have a think. So one of these has to be a hydrogen. Let's make one of these a hydrogen as well. And then we've got 5 carbons altogether. So, but we need also to have a chiral carbon, and we need to have an alcohol group. So say we put a carbon here. This carbon, we can try to make it chiral. So we're going to have 4 different groups. We know we've got an OH. We could put a H. So we're going to put a CH3, it's always our next choice. So that's 1, 2, 3, 4. So then we'd have to have our 5th carbon here. Let's check the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this has got 10. This has got the right molecular formula. It has EZ isomerism. It has a chiral carbon, so it's meeting all our requirements. And now we just have to make sure that we draw the E isomer on this left-hand side. If we look at the structure at the top, my highest priority group would be the methyl and then this branched group. So this is the Z one. So I'm going to draw that one into this Z box. So we had a C that had a H, an OH, and a CH3. And then we had a hydrogen, and we had another hydrogen, and we just had a CH3. Now we're going to draw the E isomer. So when we're drawing the E isomer, I'm just going to swap around the left-hand side so that the hydrogens are now opposite each other rather than on the same side as each other, and copy the rest. Isomer J is cyclic and has an ether, this is this bit, functional group. It only has 3 peaks in its carbon NMR. So this is carbon type 1, then 2, and then these are 3. Draw 2 other cyclic isomers that have an ether functional group. So again, they have this oxygen in a ring and only 3 peaks in their carbon NMR. So we've got 5 carbons in total. What I'm going to try to do is I'm going to try to put them all in a ring. We just kind of have to play around with this So it's going to look like a hexagon, but it only has 5 carbons because one of the points is an oxygen. So these two would be the same, these two would be the same, and this would be different. So that does have 3. We're trying to get some symmetry, because the more symmetry we have, the more likely we are to reduce those carbon environments. So how else could we put these two groups on this kind of square arrangement? Let's try something else. Oops. Well, it helps if you can draw something roughly symmetrical. So before we had them both down here. Now, if we were to put one here, I couldn't put another one symmetrically, so I'm not going to do that because there's not one. What if I put one here? Where would I be able to place another carbon that was symmetrical? So I'm going to put it to this side, and we can then see that these 2 carbons are the same, and these 2 carbons are the same, and this one is different.